Good morning, students. In continuation with the oscillations, we discuss first the previous concepts what we have discussed during offline and move on to the other aspects. Simple harmonic motion with reference to uniform circular motion. So in classroom also we have derived an equation for the simple harmonic motion. A body is said to have simple harmonic motion if the acceleration is directly proportional to the displacement, which is always directed towards a mean position for a body executing a to and fro motion. So here P is a particle executing uniform circular motion and Q is a foot of perpendicular of the particle on a diameter y dash. Particle is moving along the circumference of a circle with the constant angular velocity omega. Then we have angular velocity. Omega is a rate of change of angular displacement, that is a theta by t, or angular displacement theta is the product of angular velocity into time t. So angular velocity is measured in a radian per second, whereas angular displacement is measured in radian. So theta is the angle swept by the particle when particle runs from x to p. So here particle p executes a uniform circular motion. Its foot of perpendicular q executes a simple harmonic motion. Y be the displacement of the foot of perpendicular q from mean position at a time t. A be the maximum displacement of a q, which is equals to radius of the circular path traced by the particle. So from a triangle OPQ, we define sine theta, that is opposite side by hypotenuse. Opposite side OQ is a displacement of the particle from the mean position y, and OP is the radius that equals to the A. Rewriting this equation, we get y equals to a sine theta or y equals to a sine omega t. So y equals to a sine omega t is a equation of a simple harmonic motion, though the particle is executing uniform circular motion on taking the foot of perpendicular on any of the diameter. So this equation is called equation of displacement for particle executing SHM. Note, if a particle starts from elsewhere instead of x, then y equals to a sine omega t plus phi we write. So y is a displacement, a is amplitude, omega is angular frequency or angular velocity, t is a given instant of time, and pi is called the initial phase or epoch. If a projection of the particle P executing uniform circular motion taken along the diameter xo x dash, then displacement along the x-axis is given by x equals to a cos omega t plus pi. If you take the projection on a y dash diameter, then the displacement will be along y-axis. That is, equation of simple harmonic motion is y equals to a sine omega t plus pi, whereas for displacement along x-axis, taking a foot of perpendicular on x-axis, the equation of simple harmonic motion becomes x equals to a cos omega t plus pi. Expression for velocity and acceleration for a particle executing a simple harmonic motion. So in the during offline classes we have discussed all these things. Still then we have to have refresh what we have learnt in the regular classes. So for a particle or a body executing SHM, displacement is given by y of t equals to a sin omega t, where the symbols have their usual meaning. Y is a displacement at any given instant of time t, a is the amplitude, and omega is the angular frequency, t is time. Velocity, the two velocity varies as the particle oscillates or vibrates. The velocity of the particle is not constant, it is a variable one. Thereby we do calculate the instantaneous velocity of the particle executing SHM. So velocity, that is instantaneous velocity of the particle, is written as v of t. It is a function of time. Velocity varies periodically. It is a rate of change of displacement. Displacement is a sin omega t. When this a sin omega t is differentiated with respect to time t, we do get a omega cos omega t. Let us call this as equation 1. So this equation 1 is equation for the velocity as a function of time. As time varies, velocity varies. Also, velocity at any given instant of time, v of t equals to, it is a omega cos omega t can be written as a root of 1 minus sin square omega t. Taking this a inside this root sign, we can write omega under root a square minus a square sin square omega t, that equals to omega under root a square minus a square sin square omega t. From this displacement equation, we can write it as a y square. So here velocity at any given instant of time for a particle executing in simple harmonic motion is angular frequency under root square of the amplitude minus square of the displacement. Therefore, equation 1, velocity as a function of time. Equation 2, velocity as a function of a displacement y. Note, at a mean position, displacement, that is y, is 0. Then velocity at a mean position, we can write it as omega a square minus y square. Y being 0, we can write omega root a square as a velocity equals to product of amplitude and angular velocity. So velocity of the particle is a maximum at mean position, that is v maximum equals to a omega. At extreme position, displacement y can be plus or minus a, then velocity v of t equals to omega root a square minus y square. Substituting for y as a 0 for particle being at extreme position, so a square minus a square is 0, 0, anything multiplied by 0 is 0. So velocity of the particle is 0 at extreme position. So practically you have witnessed these aspects and you have performed 2 experiments, simple pendulum as well as the load attached to the spring, and determined the force spring constant or the force constant and time period of a seconds pendulum. So in seconds pendulum experiment, when the bob of the pendulum is at a mean position, velocity is a maximum. When it reaches to the extreme positions, the velocity of the bob of a simple pendulum becomes 0. Momentarily, the bob of the pendulum stops at extreme positions and velocity is maximum at mean position. Further, acceleration of the particle a of t is a rate of change of the velocity. So acceleration is a d by dt. Substituting for v as a omega cos omega t. So acceleration Differentiating this quantity with respect to time t, we do get an expression for the acceleration as a of t equals to minus omega square a sine omega t. A sine omega t is a displacement y, so acceleration of the particle executing simple harmonic motion is minus omega square y. Here equation 3, acceleration as a function of time. So acceleration also varies periodically with the time t. Hence equation 3 is acceleration as a function of time t, and equation 4 is acceleration as a function of a displacement y. Y varies with time t, correspondingly the acceleration varies. So equation 4 is acceleration as a function of a displacement. Equation 3 is acceleration as a function of time, since angular velocity amplitude being constant. Note, at a mean position displacement y is 0, then acceleration a of t equals to minus omega square y is the expression. Substituting for y as 0, the acceleration of the particle executing simple harmonic motion is 0 at a mean position. Hence acceleration is 0 at a mean position. Further, at a extreme position, displacement y is plus or minus a. Then acceleration at a extreme positions, a of t equals to minus omega square y. Substituting for y as a, it is minus omega square a. Thus acceleration is a maximum at extreme position and 0 at mean position. Here are the nature of graphs for displacement time graph, velocity time graph, acceleration time graph for a particle or a body executing simple harmonic motion. So here displacement time graph, velocity time graph, acceleration time graph. So displacement is a 0 at a mean position. Displacement is a maximum at a extreme position. Displacement is a maximum at extreme position, and displacement is 0 for a particle executing simple harmonic motion when the particle is at a mean position. So this is the graph pertaining to the equation y equals to a sine omega t. It is a sine curve. So y maximum is plus or minus a, y minimum is 0. Similarly, velocity time graph, when the time t is 0, that is particle being at mean position, velocity is a maximum. So there is a phase difference between displacement and velocity. The phase difference is 90 degree or pi by 2. Velocity is ahead of a displacement when time t is 0. Likewise, here maximum velocity v is a omega, maximum velocity v is a omega, and at a extreme position the velocity is 0, and mean position the velocity is maximum. Acceleration time graph. If displacement is in one direction, the acceleration is oppositely directed with displacement. If displacement is upward, acceleration is downward. If displacement is downward and acceleration is upward, so when time t is 0, the acceleration is a particle being at a mean position, the acceleration is 0, and when the particle reaches to the extreme position, the acceleration becomes maximum. So a maximum a maximum uh, so here I have made a small correction. So uh, acceleration is a 0 at a mean position and maximum at a extreme position. So a minimum is a 0, that is at a mean position, and acceleration is a maximum at a extreme position. The phase difference between displacement and acceleration is 180 degree or pi. The phase difference between displacement y and velocity v is pi by 2 or 90 degree. The phase difference between displacement y and acceleration is pi or 180 degree. The phase difference between velocity and acceleration is pi by 2 or 90 degree. Further, force law and force constant or spring constant. So in the laboratory you have performed this particular experiment, that is a load attached to the spring, and you have determined the spring constant or the force constant. So expression for angular frequency or velocity. A particle or a body executing a simple harmonic motion, the restoring force is always directly proportional to displacement, and this restoring force is directed towards mean position or equilibrium position according to Hooke's law. Consider a particle or a body of mass m executing simple harmonic motion with angular frequency omega, that is load attached to the spring. If it is pulled and released, then the load oscillates about the mean position. Then from Hooke's law, the restoring force is directly proportional to displacement y, or F equals to minus ky, where k is proportionality constant called the force constant or spring constant. If a load is pulled to the greater extent, displacement becomes large, the restoring force also becomes large. So as the displacement increases, the restoring force also is going to increase. But both the restoring force and displacement are oppositely directed. Here K is called the force constant or spring constant. The negative sign signifies that the restoring force and displacement are oppositely directed. From Newton's second law of motion, force equals to the product of mass and acceleration, ma. Already you have deduced a relation for acceleration. Acceleration can be written as minus omega square y. Substituting for a, we can write restoring force F equals to minus m omega square y, since acceleration a equals to minus omega square y. So from these two equations, equation 1 and equation 2, from equations 1 and 2, we can write k equals to m omega square. Here f equals to minus ky, here f equals to minus m omega square y. So m omega square is equals to k, or k equals to m omega square. So rewriting, we get omega equals to root k by m. Omega is angular frequency or angular velocity. It is the ratio root of a ratio of a spring constant or force constant to the mass of the particle or a body. Further, the angular velocity or angular frequency is 2 pi by capital T, or capital T equals to 2 pi by omega. Substituting for omega, that is root k by m. We can write expression for time period t equals to 2 pi under root m divided by k. And the linear frequency is a reciprocal of the time period. So linear frequency nu equals to reciprocal of time period t. So uh, linear frequency equals to 1 by 2 pi under root, it is a k by m. Conservation of energy in a simple harmonic motion. A particle or a body executing simple harmonic motion has both potential energy due to displacement from its mean position against the restoring force, and kinetic energy due to its velocity. Consider a particle of mass m executing simple harmonic motion with amplitude a and constant angular frequency omega. Let y be its displacement from a mean position at any instant of time t. Then we have an equation for displacement y equals to a sin omega t, and for velocity v equals to omega under root a square minus y square. Potential energy is a work done in a displacement of the particle or a body from a mean position to some arbitrary position, that is y equals to 0 to y. Therefore potential energy u of t, potential energy also periodically it varies, kinetic energy also periodically varies. So potential energy you can write half ky square, where k is the force constant of the spring constant, and this potential energy is half m omega square y square, since k equals to m omega square. So potential energy at any given instant of time, it is half m omega square. Instead of y square we have written a square sin square omega t. So the potential energy as a function of the time. Now note number 1, at a mean position displacement is 0, potential energy is 0. So here substituting for y as 0, the potential energy becomes 0, or potential energy is a minimum at mean position and maximum at extreme position. At extreme position y equals to a, then potential energy u of t equals to half m omega square. Y square is we have written as replaced with a square, since y equals to a. Further, kinetic energy of the particle. The particle or the body executing simple harmonic motion possesses a kinetic energy because of the velocity. The expression for kinetic energy at any given instant of time is k equals to half mv square. K equals to half another relation omega square a square minus y square, substituting half m omega square, substituting for v is velocity, it is v equals to omega under root a square minus y square. For v square it is omega square, and root gets cancelled, that's why a square minus y square, half m omega square a square minus y square. So kinetic energy is a function of time, it is half m a square omega square cos square omega t. So v square can also be written as a square omega square cos square omega t. Note number 1, at mean position displacement y is 0, so kinetic energy is a maximum. For substituting y is 0, here the kinetic energy becomes a maximum, that is half m a square omega square. At a extreme position displacement is equals to amplitude, then kinetic energy is a minimum. The particle or the body momentarily stops at extreme position, velocity reduces to 0, thereby kinetic energy becomes 0 at extreme position. Energy is a scalar quantity, it can take only positive values. Kinetic energy and potential energy vary periodically with a period t by 2 and frequency double the frequency of a oscillation. Both potential energy and kinetic energy are interconvertible. Total energy of the particle as executing SHM is constant. Expression for time period of oscillation of a mass attached to a spring. Here we have considered a spring attached with a load of mass m. When it is pulled and released, it executes the to and fro motion about the mean position. Time taken to complete one oscillation is time period. Number of oscillations made in 1 second is called frequency. When it is pulled, applied force acts downward, the displacement is downward, whereas the restoring force is upward directed towards mean position. So we have to derive an expression for the time period of oscillation of the load attached to the spring. For that, consider the oscillations of a block of mass m attached to a spring. A block of mass m attached to a spring. From Newton's law, F equals to ma, that equals to minus m omega square y, since acceleration is a minus omega square y. The magnitude of the restoring force on the mass is directly proportional to the displacement and acts in the opposite direction. The magnitude of this restoring force is directly proportional to y. More the y, more the restoring force. And y is in a downward direction. Displacement, if it is downward, the restoring force is upward directed towards mean position. So the magnitude of the restoring force on the mass m is directly proportional to displacement y and acts in the opposite direction. Here y is in downward direction, f is in upward direction. Therefore, here F is directly restoring force, F is directly proportional to displacement y, or F equals to minus kx. The negative sign signifies that F equals to not x, let me write it as a y. We have taken displacement along a vertical direction. F equals to minus ky. So from equations 1 and 2, here f equals to minus m omega square y, here f equals to minus ky according to Hooke's law. From equations 1 and 2 we can write k equals to m omega square, or omega equals to root k by m. Root k by m. Time period of oscillation t equals to 2 pi by omega, that equals to 2 pi. Substituting for omega as a root k by m, it becomes root m by k. Note, when two springs are connected in parallel, so these are the two diagrams. The springs are connected in parallel. These two springs are also parallel. These two springs are also parallel. The time period t equals to 2 pi m divided by kp. Kp is force constant for parallel combination of the springs. For parallel combination, Kp is K1 plus K2, where K1 and K2 are the spring constants for both the springs. When this load is pulled aside with some external force F, then here the spring gets compressed, here the spring gets elongated. Compressed spring pushes the load towards the main portion. Elongated spring pulls the same load uh, towards left. That's why both the restoring force, elongated spring and compressed spring, the forces, restoring force directed in the same direction. So F1 and F2 are the restoring forces for spring 1 and spring 2. K1 and K2 are the spring constants for the both the springs. For parallel combination, the net force constant is the sum total of force constant due to individual springs. Here the net force F equals to F1 plus F2, or that equals to, substituting for F1 and F2, it is minus K1 plus K2 Y. When the two springs are connected in a series, one after the other, K1 and K2 are the spring constants, F is the force, and the time period is given by 2 pi m divided by Ks. Ks is the net spring constant for the springs connected in series. So here the restoring force for both the springs is upward, displacement is downward. Displacement is downward, whereas the restoring force is upward. For the two springs connected in series, the net or effective force constant, we can define it as reciprocal of the effective force constant is equals to the sum of the reciprocals of the force constant for individual springs. Here F equals to minus K1 Y1, that equals to minus K2 Y2. Therefore, the restoring force can be given as minus K1 K2 divided by K1 plus K2 into displacement Y. Thank you.